Hello everyone, I am Dhiraj Madan and welcome to this new lecture series on physics for IITJEE. Today we will be starting a new topic which is called as electrostatic conductors. So this is essentially the part of the chapter on electrostatics. But we are only looking at electrostatic conductors in the next few lectures. And so essentially this assumes that you have already studied some parts of electrostatics already, which means that you have already looked at the idea of Coulomb's law, electric field, Gauss's law, potential, electric potential, and you also know how to what is a field line, what is an electric field. So all those things are assumed in this sort of series of lectures on electrostatic conductors, right? So today's topic will specifically deal with the electrostatic conductors, and this is the first lecture in the series. So you already have some idea about what is conductor versus an insulator, right? So a conductor is a material which allows the flow of electricity, you can say, and more specifically and it is the definition which will be useful for electrostatics, is that conductor or a conducting medium is essentially a material having abundant supply of electrons, right? So it's a material with abundant supply of electrons. So by abundant I mean that I have as many electrons as I want, I have those, right? And these are free to move, so these electrons must be free to move. Okay, so what does this mean? So let's say that you have a collection of these atoms, right? So basically metals, for example, are considered to be good conductors. So let's say you have all these sort of atoms which consist of their positively charged nuclei, right? And then they have their corresponding electrons. So these electrons, we assume that they are sort of free to move around. So these electrons, they can move freely over the layer of these positively charged ions or positive nuclei. So basically the outer electron is usually free, so you can consider that there are these positively charged ions, and then there are these free electrons which are free to move over the surface. Okay, so essentially you can have now so theoretically you can have an infinite supply of electrons. But practically this is not always possible, but essentially a practical conductor will still have some abundant electron, right? So ideal conductor is one which has infinite supply of electron. Now in the context of electrostatics, right, so we are not dealing with electric current, but why these conductors are important is that because they have some special properties, due to which if you want to figure out how the charge is distributed over the conductor, or how much is the electric field due to those charges, you will need to ensure that you satisfy all these properties. So these properties will help you determine that. Okay, so what are these properties? What are all the properties of conductors in electrostatics? Okay, so the first property is that so of course, so note that we are saying conductors in electrostatics, right? So essentially that word is also important, because in general all these properties may not always be true, but they might be true in the static condition. So let's see what these static conditions are. So static condition means that things have stabilized, and then the system is now at in a stable situation, right? It's at rest. So first thing is that the electric field is 0 inside the conducting medium. When I say the conducting medium, the outer surface, right, so that may not have the electric field being 0, but the inner core material of a conductor must have 0 electric field. Why is it the case, right? So if you think about it, so essentially if the electric field is, let's say, non-zero, right, so we look at it at two levels. So at first level, if we see, so if electric field was non-zero, right, then essentially the free electrons would move, which means that there is no electrostatics. Okay, but what if there is an electric field, there is an external electric field, then what's going to happen? Okay, so we can also look at it in a slightly different way. So let's say that you have some sort of a conductor. Okay, and let us say that there is some external electric field. Okay, so there is some external electric field E0 which has been switched on, right? So initially what's going to happen is that electric field will also start affecting the sort of electrons which are there inside this conducting medium, and these electrons are negatively charged, so which means that they will experience a force in a direction opposite to that of the electric field, right? So there are some electrons here. So this electron, this experiences a force which is opposite to that of the electric field, right? Because they are negatively charged. So force is equal to charge times the electric field. Charge is negative, so the direction of the force is opposite to the electric field, which means that now all these electrons, they are going to move in a direction opposite to the electric field. So what's going to happen is that your electrons will start, the electrons in the medium will start accumulating on the left side of this conducting medium, right? This is assuming that the electric field is from left to right, so they'll start accumulating in the opposite direction, and in the process they leave essentially positively charged ions on the right surface. Okay, so essentially the force experienced is minus of E times electric field. Minus E is the charge which is opposite to electric field. So essentially the electrons accumulate on left surface, which is now negatively charged, and leaving a positively charged right surface. Okay, so essentially now what's going to happen is that now I have these sort of charges, negative charges on the left, positive charges on the right. So these charges are going to create their own electric field, right? And we know that positive charges are the source of the field, negative charges are the sink. So essentially there is another electric field which is created, which is in a direction opposite to E0. So I'm calling this E1, right? And essentially now what's going to happen is that there is this sort of opposite electric field which has been created, and now until when will this movement of these charges go on? So essentially the more the charges move, the more the positive charge accumulate, the more the positive charges accumulate on the right and negative charges on the left, the higher is the intensity of the electric field which is created, right? So movement of electron continues until the charge inside the medium, which is E1, completely cancels E0, the electric field which is inside the medium, that completely cancels the the external electric field inside the medium. Externally, there will be some electric field which is created due to these charges. There is some external electric field as well, but they may not essentially cancel overall. But inside the medium, they will cancel, and once they cancel, then essentially the further movement stops, and we reach a stable static condition, right? So essentially, this sort of the separation of charges which gets created. So this is called as electrostatic induction. Actually, something similar also happens when you perform that experiment, right? In your childhood, you would have done that experiment that if you rub a ruler on let's say on a head, and if you have some bits and pieces of paper, then the ruler starts attracting those bits and pieces of paper, right? The ruler or the scale that starts attracting those bits and pieces of papers. So what's going to happen is that although the ruler you get that gets charged by friction, but essentially those bits of paper, they are still uncharged, right? So why do they get attracted to the ruler, you might have thought. So the answer is that there is still something similar, that charging by induction which goes on is that the negative charges accumulate on the one side of the paper and positive charges on the other side. Overall, those strips of or bits of paper are still neutral, but essentially they have a separation of charges, and essentially the one end of those charges is attracted to the ruler, and that's why they get lifted. So okay, so just think about it again, okay, and something similar happens there. So that's something I wanted to tell you. And next, the next property. So this was the first property we have studied. So the next property is that, so this is property number 2. So there is no charge in the interior of the conductor. So first property we studied was that there is no electric field inside the conducting medium. The next property is that there is no charge in the interior of the conductor, right, or inside the conducting medium. So note that this does not rule out the charge on the surface. On the surface we can still have charge, but in the inner core material there can be no overall charge. Why is that? Because if there is going to be, let us say there is some charge, okay, some charge Q. Right. Now let's consider a small sort of a Gaussian surface around this charge. You can consider like a small spherical surface which encloses this charge, and such that that entire sort of that surface, or the volume enclosed by that surface, that happens to lie inside the conducting medium, right? So this point was inside in the interior of the conductor. That is why we could construct such a surface. Now if we apply Gauss law, what do we get? We get that integral of E dot dA equals Q enclosed over epsilon naught. And this Q enclosed, if we have, so essentially now integral of E dot dA, right? So we have just seen that inside the conducting medium there is no electric field, so this part is going to be just 0, right? So if this is 0, then we can see that the Q enclosed, the net charge enclosed in the surface, must also be 0, right? So there can be no charge inside the conducting medium, right? Because essentially if there is charge, there is going to be essentially some sort of electric field. You can think about that, right? Because if there is some charge, then integral of E dot dA must be non-zero, right? But integral E dot dA is 0, so therefore Q enclosed must be 0. Okay. So in other words, you can say that rho equals to 0, or the charge density equals to 0 inside the conducting medium. Okay. So this argument is not applicable to surface in the sense that on the surface you can still have some charges, but in the inner material there cannot be any charge. Another way to look at it, right, this same property too, I can think about it in another way as well. So another perspective, let's see on property 2. So what's this other perspective? So essentially the idea is that if you have any charge, let's say positive or negative, right? So if you have positive charge, then essentially there are field lines which can accumulate, which essentially go outside the charge, right? And because any sort of charge must be a source of electric field lines. But essentially electric field lines, if there are there, then essentially the neighboring electrons will experience force and they'll move, and hence there won't be a sort of the static condition, right? So there must be any charge must be a source or a sink of field lines. So this is impossible inside the interior of the conducting medium, right? Because inside the conducting medium there is no field and hence no field lines, right? So this is impossible inside the medium. Right, actually in the diagram you can also look at the case of, what if there is a minus q charge, then that will be a sink for these field lines. And essentially we rule out both these conditions. Neither there can be a source nor there can be a sink of electric field lines inside the conducting medium. Okay. Next we look at the property 3. So property 3 says that any charge can reside on the surface of the conductor only, right? Because it cannot reside in the interior. So therefore any charge must reside on the surface of conductor only, because it cannot reside in the interior. So essentially this is just a restatement of property 2, that if there is some charge, then we know that by property 2 it cannot reside in the interior of the conducting medium. Therefore if at all there is, it must reside on the outer surface. Okay. Next we have is the fourth property, which states that all points on the conductor are at equal potential. And this is true for both surfaces as well as the inner conducting medium. So all points on the conductor are at equal potential. Why? Because let's take 2 points, okay, P and Q. Now we consider the line joining the point from P to Q. Now we know that the potential at Q minus the potential at P, what exactly is it? So that is minus the integral of P to Q E dot dl. And since the electric field inside the conducting medium is 0, so the electric field is 0 along this line. So therefore this also must be 0. Right. In general, even if you can't find if this direct line joining them is not part of the conductor, then you can take some path, right? So let's say if your conductor was something like this, and if your points P and Q were here and here, then you cannot take the straight line path, because that will go outside the conductor. So what you do is that you can take the curved path, But again, you can apply that same integral E dot dl logic to say that Vp minus Vq must be 0, or in other words, the potential at P must be equal to the potential at Q. And this is true for any two arbitrary points. So all points inside the conductor have the same potential. Now let us look at the property 5. So property 5, what it says is that outside, right, the electric field, outside the conducting medium, let's say just outside the surface, how much is the electric field? And the idea is that this must be, we will calculate the quantitative amount in maybe in one of the next few lectures, but what we are saying for now is that just outside the surface, the electric field must be perpendicular to the surface. So let's write it down. So electric field outside the surface must be perpendicular to the surface. Electric field just outside the surface, I should say. Okay. So if I have this sort of a surface, then just outside it, the electric field must be perpendicular to the surface. There cannot be any component which is along the surface. Why is that so? Because let us say if the electric field just outside the surface is in some other direction, let us say it's not perpendicular but it has some direction parallel to the conducting surface as well, right? Then essentially electrons near this point, what's going to happen is that they'll experience a force in this direction, and since they can flow along the conductor, they'll start flowing in the direction opposite to the electric field. So essentially they'll start flowing. So this experiences a force. If the electric field is along this direction, then it will experience a force in the opposite direction, and hence the electron will be able to move along this direction. Okay. So basically if it experiences a force along this direction, then it will have some component perpendicular, it cannot move there, but the charges can move in the direction which is along the direction of the direction parallel to the surface of the conductor. They can move, right, because electrons can move along a direction parallel to the surface of conductor to cancel the field, right? Or maybe experiencing the force, they can move along the direction parallel to that of the conductor until that component cancels off. That is one argument. The other argument is that we have already seen that the points are at equal potential, right? So essentially, if there is some sort of electric field along a direction which is sort of parallel to the surface, then essentially this E dot dl, right? So if E is perpendicular to the surface, then E dot dl components are 0 along this path. But if it has some component along this path, the path which goes along the surface, if it has some component, then essentially the points will not be at equal potential, right? So this is one reason, is that the electrons can move along the direction which is parallel to the surface until they cancel off. So basically this is not possible. The other reason is that the electrons so the other reason is essentially more mathematical reason, which you have seen from property 4, which is that otherwise integral E dot dl along the path is non-zero, and hence Vp is not equal to Vq. When I say along the path, which means that along the direction parallel to surface, the component parallel to surface, it's non-zero, hence Vp would not be equal to Vq. Okay. So all these are the properties which we have seen so far. I would like you to sort of read them again and try to think about them and reason for yourself, right? Until these become like second nature to you, right? Because you should not have to reason out these arguments again and again. You should actually now remember these properties so that you can apply them whenever you need. But we'll also see some problems based on these. So these problems themselves are some sort of theoretical concepts in their own right. So let's see these sort of problems now. So let's see the first problem. So a conducting solid sphere has a total charge Q Now, what is the electric field and potential at points inside and outside the sphere? Right, that is the question. Okay, so let's try to solve this problem now. Okay, now first of all, since the charge Q cannot reside on the conducting medium, the entire charge must flow on the surface, right? So basically, let's first draw this figure, right? So basically, this is a conducting solid sphere. Okay, so this is solid. Okay. This is not a hollow sphere, this is a solid sphere, and we are given that the total charge is Q. Total charge on this sphere is Q, right? And we are asked to find the electric field and potential at points which are inside and outside the sphere, right? So first thing is that all the charge must lie on the surface. Why is it so? Because we have seen by property 3 that any charge on the conducting material can only lie on the surfaces of the conducting material. It cannot lie in the inner core region of the conducting medium. So essentially all this charge Q now flows to the surface. Okay, so now it flows outside and it lies on the surface, and now we are being asked and how will it spread? So it is by sort of symmetry. It spreads uniformly by symmetry. So we can assume that the radius of this conducting sphere is capital R. So essentially the charge density is Q over 4 pi R square. So there is a net charge of Q which is on this surface now. And now we need to compute the electric field on points which are inside and outside the sphere, right? So if you take any point, let's say outside, right? So this now we can apply the same Gauss's law argument. So for R greater than R, you can apply Gauss law and check that integral of E dot dA on a surface of radius small r, on spherical surface of radius small r, must be equal to q over epsilon naught. And so if you have some spherical surface of radius small r, then essentially the electric field at any point must be along the radial direction firstly, right? Why? Because the longitudinal direction, they will all cancel away by symmetry, so it must be along the radial direction. And if you compute now integral of E dot dA, so you will get the magnitude of E times 4 pi r square, that equals q over epsilon naught, which means that this electric field is q over 4 pi epsilon naught r square, right? And this is something you have already expected as well, right? In general, for a hollow sphere of radius capital R, the electric field outside is simply q over 4 pi epsilon naught r square. So although this is a solid sphere, but since the charges have accumulated on the surface, so its behavior is very similar to that of hollow sphere only. And similarly for r less than equal to small r, right, or strictly less than small r, what we have is that we can again draw the sphere. So all the charges are now outside on the surface, right? And if you draw a sphere of radius small r, which is less than capital R, right, then essentially integral of E dot dA must equal q enclosed over epsilon naught. So essentially that is going to be 0 because there is no charge enclosed. And this integral of E dot dA, again, if at all there would have been some electric field inside, it would have the direction would have been along the radial direction only. So this would have been mod E times 4 pi small r square, but we see that mod E must be 0. Right? So the electric field is essentially 0 if small r is less than r and q over 4 pi epsilon naught r square r cap, right? So this is inside the sphere and q over 4 pi epsilon naught r square outside the sphere. And note that we already expected that it is supposed to be 0 inside the conducting material. So this was already expected from property 1 also, right? In fact, when we derived the fact that all the charge in the inner material must be 0 and all charges must be on the surface, we derived it from property 1 only, which says that the electric field in the inner conducting medium must be 0, right? And now let's calculate the potential at points inside and outside the surface. So we know that the potential at any point minus the potential at infinity is just minus integral of infinity to r E dot dr, right? V infinity is just 0, so essentially Vr is just minus infinity to r E dot dr, right? And now if you integrate it out, it's essentially q over 4 pi epsilon naught r, right? If r is less than r, and q over 4 pi epsilon naught small r if r is greater than equal to r. Right? Because once you reach the surface, then essentially the potential is all the same. So you can check that inside the spherical surface, the potential is also the same, right? So this you have also seen from the property 4, right? So that's it for today's lecture. Do revise all these properties, and we'll see some more problems in the next lecture. Thanks a lot.